telemóvel.
Vai lá falar. Mas não está a chegar aqui.
Teste, teste. Olá, bom dia.
Jonathan, can you hear us? I think we still don't have your sound.
Hey, can you hear me now?
Yes. Welcome. So if you can try sharing your slides to see if everything is working.
Yeah, let me try and do that. This work?
Yes, but the left side is cutting a little bit. It's not centered.
Okay, I'm not sure how to change that. I've just shared the screen.
Oh, that's better. Okay.
That's better. Okay, but this isn't in screen share, so you'll see all the surrounding parts of my slides. Is that okay? Because when I put it up to full screen, it seems like it clips for some reason.
Okay, can you just try again the full screen? Because maybe it was a setting here. Now it's better. Yeah, now it's perfect.
Okay.
Maybe it was a setting from the room.
Okay.
Okay, so welcome back, everyone. This is the last day of our Machine Learning for Science and Engineering Summer School. And it's my pleasure to introduce Jonathan Godwin. He's currently the CEO of a startup called Orbital Materials, which is working on AI discovery of new materials. And prior to that, he was a research engineer at DeepMind, where he did some of the pioneering work related to modeling physical systems using machine learning. So I think in one of the sessions earlier this week, you saw that graph neural network to learn from simulated fluids, so from the technique of smooth particle hydrodynamics. Jonathan was in one of the authors of that paper. And he also has research on predicting properties of molecules and materials. So really excited to learn from him. So Jonathan, you have the stage.
Thanks so much for having me. I'm sorry I couldn't be there in person, but I'm glad to be presenting nonetheless. So I just wanted to start. I think there's so much in AI for molecules and engineering things on the atomic scale that is so focused on biology because, of course, if you solve problems in biology, you get to cure cancer or do any number of incredible things. And it's a very natural application for AI applied to molecular sciences. But there's a whole other area of atomic engineering that I think has equal opportunity for impact. It's impact via a different route, but I think it potentially has even more opportunity than AI for pharma, and that's AI for advanced materials. So when I use that phrase advanced materials, I'm really talking about not things like sustainable leather or construction materials or steel or anything. I'm talking about things like semiconductors, electronic materials with weird electronic states, solar panels, carbon removal materials, things that are very highly engineered, very difficult to make, but really underpin, I think, a lot of our day-to-day life. And AI, in the same way that it has changed the way that we design molecules in biology, has changed the way that we design advanced materials. And there are two key ways in which we achieve this. There is AI accelerated simulations, which is, I think, very similar, to the theory of change in AI for engineering simulations. That if we are able to increase the speed and the scale of a simulation, then we can model systems more accurately. We can simulate an entire protein rather than just a slice of it. Simulate proteins interacting. Simulate large chemical reactions happening at a grain boundary, which is something very difficult to simulate, or large mesostructures like porous materials. And the speed allows us to then look at longer term effects happening. So, increased simulation, I think, has been a real focus area for AI applied to advanced materials development. It's an area that the Orbital has put out the majority of our public-facing work, and has seen a huge improvement and development over the course of the last few years. The second area, which I think is the future area that I'm really excited about, is replacing a screening workflow, whether that be an experimental screening workflow or a in silico screening workflow, replacing that with a generative design or a design workflow, where we start with a functional property that we care about, and we use AI to design a material that has that functional property. We've seen this work really well in proteins. We've seen this work really well, of course, in images, which in many ways have a similar, if you were to take out any semantic meaning, have similarities in some ways to the way you might think about representing a molecule or a material. And so there's no reason to believe that this wouldn't work for materials, especially bulk materials where you're interested in bulk properties. Now, this would be huge because so much of the computational, inverted commas, computational work in designing new material or finding new materials is this screening-based approach. It uses up a huge amount of resources, and I think limits us to a relatively small area of chemical search space. Using rational design instead, I think will allow us to get to materials far quicker than would otherwise be the case. The third area that I haven't really touched on here, but is actually something that I think is just as impactful, and Orbital has started to work more in, is thinking of these as tools for an scientific agent. Now, I think a lot of people have started to work on this. I think the thing that to me is missing from the incredible theory of change there, which is to have a co-scientist that can look at all the different types of data, the characterization data, the literature data, run simulations, use generative design tools to come up with new hypotheses and then go and run those experiments, is building an organization and building a lab from the ground up with that in mind. I think once you start thinking, well, how do I best do that integration? And can I even change the way that my lab is run, my data architecture, the way that I gather and represent data to an AI agent? If you're able to change everything there, then I think that you'll start to really see those huge benefits. And so I'm really bullish on that as well. But in this talk, I'm just going to be speaking, I think, about these two areas, which I think have formed the crux and certainly the majority of published literature about AI for material science. So I should say that these methods are already working. At Orbital, although I could have used examples from any number of labs here, this isn't a Orbital specific thing. At Orbital, we were able to use our accelerated simulation models to discover a new mechanism for potassium transport in cells. So there's something called the potassium ion channel. This is a protein complex, and it selectively allows potassium to enter a cell, but nothing else. It's in a large majority of the cells in all biological life, but the way it works has never really been fully understood. It's always been a bit of a mystery because it's really hard to simulate and it's really hard to experimentally characterize. It's hard to simulate because potassium is a metal, the proteins are organic molecules, and they're very big. So if you wanted to simulate it, you would need something that stretched across the periodic table that would be able to take into account interactions of metals and organic molecules. you would need that to be high accuracy, and you need to be very fast to take into account the scale of the simulation that you would need to run. Now that has just not been possible to do up until now. It certainly has been possible for a bog standard research lab to do, because if you were to try it with classical methods, with classical bottoms-up physics simulations, that would have taken months or years. But this was run on a single NVIDIA V100 GPU. We've put this out as a paper now, and we're working with folks to try and see if we can experimentally verify the predictions that this made. Here are some videos of different simulations that you can run. So this is a 500,000 atom simulation of a COVID spike protein. This is run on a single GPU at what you call ab initio accuracy. So this is taking into account all the crazy quantum interactions that are going on between this protein, COVID spike protein, and its surrounding water solvent. This would just have been impossible a few years ago, but again, run on a single GPU. And this is using Orb Force Field, which is our AI accelerated simulation package. And this is a simulation of a sound wave moving through a uranium crystal. So again, uranium's a very unusual metal. It's very hard to simulate classically because of its unusual quantum properties. But here you can see that we can run and we can simulate a very large uranium crystal with a single GPU as well. Yeah, and finally, this is an example of a chelation interaction happening. Chelation is where you have a metal. Maybe you're trying to extract gold or remove a metal from a liquid stream, and then you have an organic molecule that will react with that metal, and then that's the way that the separation happens. Again, a really hard thing to try and simulate, because you need to understand the reactions across the periodic table, the interactions across the periodic table, and that's very challenging to do. Requires a lot of computational resources to do the classical way, but using AI accelerated simulations to replace that classical force field, you're able to get really high accuracy simulations. And so there are two ways in which that performance improves. The first one is to think about large timescales. So if you were to take just a kind of small system, a lot of the things that we care about in chemistry and material science take place over the nanosecond or millisecond timescale. If it takes you half an hour to calculate the energies and the forces of a single system, put that into a numerical simulation system, a molecular dynamics package that's going to run as a I can't even remember now, it's like something like femtosecond, then you've got quite a lot of time to wait, way too much time to wait, to ever get to observe one of these rare phenomena or these long timescale phenomena that are so important to the real application of that material. So much so that it becomes pretty implausible to do that. And the sorts of things that I'm talking about there are things like bond breaking and forming in a chemical reaction, framework flexibility in a porous material. How does it change under certain conditions? There are so many different things that fall into this long time scale category that would otherwise be really impossible for us to start to simulate, but now become possible through the use of AI accelerated simulation. The second thing they're able to do is increase the size of the simulation. Now, this is super important for let's say that you have a chemical reaction happening, and this chemical reaction requires coordination between tens of different atoms, tens of different molecules, and it's all happening on a catalyst surface. That sort of thing, it has tens of thousands or hundreds of thousands of atoms. Or if you're thinking about interactions between large proteins and metals, that happens all the time in the body. That's a really important thing for us to be able to study. But that, again, needs tens of thousands, if not hundreds of thousands of atoms to properly represent. Now, I think that what we're now able to do through the use of these AI accelerated simulation engines is take what would have been a 100 atom system and scale that up to 500,000 atoms on a single GPU. So an order of magnitude higher fidelity in terms of the systems that we're able to run, able to take into account all of the different aspects that we would care about. And if you were to run that on multiple nodes, you'd be thinking about perhaps 4 million atoms, on multiple GPUs, you might be thinking about 4 million atoms per node. So that's 8 GPUs on a single node, which is an extraordinary level of scale for what is now a pretty, easily available computational setup. You don't need to go build a supercomputer at your university to run this scale of simulation anymore. I think that's a huge unlock for computational material science. Now, these are some results from our most recent AI simulation package called Orb v3. And it goes to show that for the very first time, you can simulate 100,000 atoms at quantum chemistry on a GPU through the use of Orb. But I think the thing that is quite incredible here is to see the significant improvement over time in the performance characteristics. So I think about 6 months ago, that's when you looked at this gray bar here, and you were looking at quite a long inference time and quite a large memory usage to achieve the very best accuracies. Now, over a kind of 6-month period, that's declined, by sort of 5x, which is quite incredible. If that continues to decline at that sort of rate, you're really getting into a totally new paradigm of what it means to do accelerated simulation. So this is a field that's moving incredibly fast. It's moving, perhaps as fast as the LLM field. Obviously, it's a more niche application. Fewer people do research into this area, but the lingering effects of the huge advances and the engineering effort that has gone into improving utilization of GPUs, improving GPUs, bringing down those costs, start to filter back and have long-lasting impacts on engineering and on science, areas that by themselves are probably too smaller markets to justify that sort of investment. So I think we as a community working on AI for science and engineering benefit immensely from what's happening in the LLM field, and we should continue to see those benefits filter through into our applications. I used to have this slide. I'm very sad. Actually, I don't know if you've been following. This slide was from an economics academic article that purported to show the impact of using generative AI on new materials discovery. This paper has now been retracted by MIT because the person who wrote it made some of these figures up. But I believe in a few years' time, if you were to actually track the impact, then it would look something like this. While I'm very sad that this is made up data, this in the future I'm sure will be real data, because at least at Orbital we see the impact of using a lot of these tools day to day. So what do we do? I mean, I think it sounds to me like you have already heard during the course of this summer school graph neural networks, and so I don't necessarily need to introduce those to you, but suffice to say that we use graph neural networks, and the community uses graph neural networks for simulation applications. I think that at some point, and it's something that I love talking about, which is when is the homogenization that seems to have happened across natural language processing and images, when is that going to start filtering through into, and it seems to have happened in proteins as well. AlphaFold is a transformer architecture. AlphaFold 3 is a vanilla transformer architecture. When would we expect to see that start to happen in simulation and materials and molecules? I think it will happen, is my personal view. I think it will happen relatively soon, but you will make some sacrifices by moving to a transformer. It's not a free lunch, as it were. You'll lose something by making that move. But for the time being, we're using graph neural networks. And so they work in a very similar way to the way they work for particle fluid simulations, which is that you construct a graph from your particles. In this case, those particles are atoms. That graph has nodes as atoms, and then the edges are the vector displacements. So you just take the positions of two connected atoms and you subtract them, one from the other, and that will give you that vector value, which is what the value of the edge. During computation, you compute first a latent representation, use a neural network to compute a value for your edges. These are then passed to your nodes, and then your nodes take in that message and the atom value. So, in natural language, I think the sort of reasoning that goes on is to say, I am 1 angstrom away from a carbon atom, and I'm an oxygen atom. What do I think the interaction between that carbon atom and myself is, and which direction is it pushing me? And so that is the sort of computation that happens during that propagation step. And you do this multiple times, and those multiple times learn higher levels of abstraction on the sorts of messages that are being passed and computed. And we benefit quite a lot, and the community benefits quite a lot from NVIDIA's work on building special libraries that enable this sort of computational pattern to work really well for molecules and for their GPUs. One sort of difference between this and a sort of neural network, a graph neural network that's used in engineering applications, is that physicists and people who really care about chemistry really care about preserving mathematically, with a guarantee, the physical properties of the system that they're modeling. And so some of those physical properties are things like invariance to translations of the positions of your atoms. If you move it to the right, the forces that are interacting on those atoms also move to the right. They don't change. They're still, I'm pushing in this direction by a certain force per angstrom. So your system should be invariant to translations. It should also be equivariant with respect to rotations. So your forces, when you rotate, if you were to take two atoms and they're just pushing against each other like a spring, if you were to rotate that spring, those forces would be operating in a rotated direction, right? So they're pushing against each other here, they're pushing against each other in a perpendicular direction if you rotate it 90 degrees. So that's a mathematically guaranteed, physically enforced property of interactions with at the atomic scale. And people really care about preserving those in their neural networks. And so what that means is there are certain types of mathematical operations that are guaranteed to do that. Those would be called, invariant or equivariant operations as part of group theory. And it turns out that a lot of the traditional things that you would use for a transformer or a convnet or a MLP, those are, unfortunately, not members of that group of allowed operations. And so we create new types of neural networks that respect those physical rules. And those are often called equivariant operations, tensor operation, certain types of tensor contractions work with this. And that then also changes the performance characteristics of these neural networks. NVIDIA, again, has worked really hard on supporting some of these operations with new libraries. And so now these sorts of neural networks are really starting to reach the sort of performance levels of a vanilla neural network that doesn't have those sort of guarantees. But at the same time, the community has worked really hard to train models that, while might not have that mathematical guarantee, at least empirically seem to obey it. So I think these kind of worlds are converging, and I think we'll see a greater level of homogenization across sorts of models and domains that use graph neural networks to something that looks pretty similar. And I think that's really exciting because I saw what the impact of that was on NLP and images. The other thing that we make a lot of use of in AI for materials is synthetic data. So we utilize synthetic data to reach unprecedented data scale with our training runs. So we can use what I described as these incredibly computationally intensive codes, existing codes, to get high quality data. And we can generate quite a lot of that. And now, that's not, you might say, well, why do you need a machine learning model if you can generate the data? Well, the computational costs and the scale of that is a lot less than we'd be able to do with AI. But what is great for us means that we have a tractable way of targeting data collection at areas that we really care about and of dramatically increasing our data scale. And a lot of the efforts in AI for materials have been around this. I think Meta has done a really great job at continuing to push the frontier of what we were able to achieve with data scale in molecules. They just released a great new data set for organic molecules, which I think is certainly the largest ever released and a really great level of theory. And I think this means that whilst at the moment perhaps we're data scarce in comparison to natural language processing and some of those other areas, we'll soon be getting to a level of data that means we can start scaling up some of these models and start scaling up some of the computation here and really reach levels of accuracy that make this indistinguishable from using a first principles simulation engine like density functional theory. So I think that's really exciting. Access to data, access to lots of data is obviously the start of taking advantage of the bitter lesson, the thing that has really driven AI for the last 10 years. So I want to use a case study now about how we put these things into practice. Orbital, we are a vertically integrated company. We don't sell AI software. We make new materials. And we use AI software internally to accelerate the development of those materials. We're really excited by that. We think it's such a cool sort of company to try and build. And so we also means that we can get to give exciting case studies of the sorts of things we're able to do. So carbon removal materials, often called sort of solid sorbents. Now these are sort of sponge-like materials that selectively capture CO2. The categories of these type of materials might be zeolites, made out of silicon, aluminium, and oxygen, MOFs, which are a combination of a metal and an organic molecule that coordinate to create these sort of beautiful, large, porous structures, or porous polymers, which are well, they're just polymers, but they've been synthesized in a specific way to give them a porous structure. Now, calculating properties of these is really hard because you need to run a simulation. These are not the CO2 absorption is not a bulk property. You can't just calculate, what's the absorption capacity of this crystal structure. You need to run a simulation to see how CO2 is interacting with that porous material and all the other things in that material, in the air that it's capturing from as well, to see what the selectivity of capturing that CO2 is going to be over capturing water or some other aspect of the gas that you're under consideration. And so you really need a large-scale and very fast neural network potential simulation engine to get that right. And that's what you see here. Like, you would never be able to do these things with classical simulation tools. But we can see that there's a really great, this kind of beautiful image here of something that is experimentally also observed, of where the blue spots are where the CO2 is interacting with this metal organic framework. You can see that this simulation is really picking up the correct areas. And more than that, it's getting the intensities correct as well. So actually the one on the right is more correct than the one on the left. The interaction is there, but it's somewhat weak. And you can able to visualize, whereabouts the CO2 is going to be sitting in its kind of minimum, most attractive spot. So these are measurements that I think are then end up being really useful tools for us to be designing and evaluating new materials classes. And so this translates into the real world. Since setting up our lab at the beginning of last year, I should say, so now 18 months in, we've seen a 10x improvement in the absorption capacity and the performance of our DAC material. So that's really great, and we're really excited to see that performance, and that's now going out into the real world at the end of the year. So future directions, materials will make the 21st century. Advanced materials is what's given us the computer revolution. There's no reason to believe that it won't underpin the next physical technology revolution, whether it be data center technologies, aerospace, energy, or climate technologies. All of those are advanced materials applications. And so a fundamental way of speeding up and accelerating the development of those products and those materials is something that could have a massive effect and massive impact on the world. And so I'm incredibly excited to be part of that journey. And that is, I think, the end of my presentation. So happy to take any questions.
Thanks, Jonathan, for this fascinating talk. We have a first question from the audience here.
Hello? Yeah. You said that before we need supercomputers, now we can do it 10 times faster. This is one of your first slides. My question is, can you do it without supercomputers now? Was it increased computer power or an algorithm improvement? This means regardless what you mean by supercomputers of today or the supercomputers of 10 years ago. Is my question?
Yeah, that statement was to say that if you replace a first principles physics simulation with an AI surrogate, that AI surrogate is going to be a lot faster from an algorithmic perspective. Now, that in order to run that first principles physics simulation, you'd have to use a supercomputer. And so when I say supercomputer, I mean a highly connected CPU supercomputer, not a GPU supercomputer. So I think there still are CPU supercomputers being built. So I think that's still an important part. But it's really a comment about what happens if you move from a CPU-based bottoms-up simulation to an AI surrogate-based simulation that runs on a GPU. What would the relative speed ups be? And they would be 10 to 100x, I would say.
Jonathan, maybe I can pick up from there and ask a related question, which is, where do you see the main source of that speed up? Is it that when you train, let's say, the graph neural network to predict your next step, you can predict a much bigger step ahead? So you predict like the equivalent of 1,000 steps of the numerical simulation? Or is it that you get around at avoiding these quadratic interactions of all particles to all particles with some sort of encoder-decoder architecture, and you would get around that problem, that quadratic?
Yeah. So I think it's actually, all of those are methods. I think if you think about, where is AI for materials at the moment, it's actually more prosaic than that, which is that just to compute the forces with sufficient accuracy is very computationally expensive. So it may take half an hour just to compute the forces.
Okay.
So if you were to increase the speed of that by 10x, then by simply replacing that computation with a surrogate that is a dense matrix multiplication rather than a non-dense, sparse, very complicated, difficult to parallelize and vectorize computation, which is what it would ordinarily be, you are able to get that speed up. Right? So it's not about
Okay.
It's
You don't predict the next positions, you do this in a classic way, but you just estimate the forces much faster. Okay.
That's right.
Question from the audience.
Hi, thank you so much. I don't know much about materials, but what is it that the physics model cannot be run on a GPU? Because we see it in like fluid dynamics that you can run those physics models on GPUs now, but with materials, like what is it in the underlying physics that it cannot be run in the GPU to compare like the AI model on a GPU versus the physics model on a GPU? And yeah, maybe like a lot has been done from NVIDIA on GPUs for AI, so like you're leveraging that, but like, yeah, how is the physics to GPU possible or not, and why? Thank you.
Yes, I think it is possible to run them on GPUs, and you do see a degree of speed up through doing that. But those algorithms are they're cubic scaling. That's nothing to do with the GPU part, but just to say that intrinsically they're going to be slower. B, they are small matrix operations. And C, they don't have this kind of very dense sequence of large matrix operations that kind of characterize, I think, what a high performance neural network look like and are very well suited to GPUs. So the combination of those three things basically means that I think there's less opportunity for really taking advantage of that GPU with classical algorithms. You do see some speed up. I can't remember exactly what it is. I think maybe it's like double to triple the speed up through moving something to GPU. I think potentially it's less depending on what algorithm you use. But it's not, I think one of the things that is incredible about has given neural networks such incredible performance has been just their great fit for the compute architecture. They really are able by design, because they're large dense matrix multiplications for the most part, they're really able, they're kind of perfect fits for GPUs. Whereas like maybe traditional scientific computing codes have some speed up, but are not in general like designed to leverage the best of the GPU hardware.
Hi, thank you for a pretty mind-blowing talk. I'm really curious about like how machine learning works so well on this like quantum scale. But I guess my main or like concrete question is, I think this week I've seen how emulators can sort of step a CFD model, like 5 steps ahead, to sort of work to be the ODE solver that kind of like steps the system sort of forward in time. But is it here used to sort of, you get the input, like the molecule, and then the output is just whether it will be stable or not, or like maybe that free energy sort of field that you showed, like, so it's just the input are the molecules, and then the output, it just tries to step directly to that? Or does it sort of try to kind of similar?
That's a good question. Yep. So I would say the majority of the field is focused on something a couple of steps before that, which is just to speed up the calculations of the forces and the energies, because those are so computationally intensive when you want to take into account the electronic structure of a material. There are people who do direct prediction, take a the data-driven approach to basically take a crystal structure or molecule and directly predict some thermodynamic quantity of that molecule. That's not primarily what we do. We've seen some success in there. I think that there's starting to be work on, in a funny way, because it's so hard to predict the forces and energies here, people have focused on that and sort of only now getting their heads around what it means to do accelerated simulation in the ways of implicit ODE solving, coarse graining, things like that. I think that is something that people are now focusing a lot more of their energy on within the area. But in many ways, we've just kind of been stuck on this problem as a field for a few years now. I feel it's kind of almost solved. So people are now looking to take in some of those lessons that we've kind of seen with CFD and other engineering simulations.
Hello, thank you for the presentation. I find it really interesting. I was wondering, like, when you managed to find like a material with very interesting properties or whatever, a new one, do we now have the capability of building this new material, or it's something that we have to wait for maybe a few years? I was just curious about the now direct applications.
Yeah, so I think, one thing that is different about material science, or difficult about material science, is you can make something at a lab scale, which has great properties, but there's not a sort of, we'll just make it at scale like we did in the lab. You got to really rethink the way you make something when you think about scaling up. And I think the second thing is that for an academic publication or for research, often you don't have a cost target. First you find the property and then you try and optimize the cost. But to get something out there commercially, you need to have hit that cost target. So it's not that cost target is not important. It's that cost target is the second thing that you optimize for. But if you don't hit it, then you don't have a product. And so it's very, it takes a while to get new products to market in materials. What we are doing, I think, has been to try and focus on manufacturable materials, areas that we know we could easily manufacture. And so, we are hoping to get that material out into the market as part of a carbon removal system that we're selling. So we sell the whole thing actually, but as part of the system, you know, end of this year, early next year.
Okay, thank you.
Any more questions from the audience? All right, so let's thank Jonathan Godwin again for this fantastic and inspiring talk.
Thanks so much.
Okay, so we actually now have a break that is a bit longer than usual, I think almost an hour or so, because this one finished a bit earlier. So the last talk will actually be given by myself, and it will be at 11:45. For me, I could start earlier, but this is on the schedule everywhere and so on and on internet, so it would be surprising for people connecting online if we'd start earlier, so let's stick to the schedule. Nobels, I guess. Okay. Okay, so welcome back, everyone. Uh, this is the last session on our machine learning for science and engineering summer school. As you noticed, even though we had a broad title, we talk about applications of machine learning for science and engineering, because of the target audience, because of the PhD students that were here, this was mostly biased to applications that had some connection to computational fluid dynamics, perhaps with the exception of the previous lecture, which was focusing on material science. So what I wanted to do in this closing session is give you like a broader overview of the impact of AI in science. And I gave this title to the talk, which was, will there be more Nobel Prizes for AI? And I mean, I gave this title because very famously last year, there were 2 Nobel Prizes attributed to contributions from AI, so in physics and chemistry. But obviously this title, or this question is way too easy, right? Like, the likelihood that in the next decades, there will be, you know, dozens or hundreds of Nobel Prizes and none of them will be attributed to any breakthrough from AI, it quickly vanishes to 0, right? So the more fair or the harder talk for me, it's actually being a bit more specific and trying to predict what will be the next Nobel Prizes given for AI contributions, right? So there I can be wrong, right? I can be wrong in my predictions. And so the way I will go about it is to start by giving you an overview of how, what were these recognitions given by the Nobel Prizes in physics and in chemistry, and then looking ahead. So most of this is, or like looking ahead, I'm gonna talk about work of other people, right? Especially of the group at DeepMind that focus on these science problems. And that's not my work. The only contribution, small contribution I had was at the initial phase of AlphaFold, so that was the Nobel Prize on Chemistry in 2024. And on that one, I can tell you a little bit the story because I was there to see the beginnings of it. So the one in physics was attributed to John Hopfield and Geoffrey Hinton for the foundational discoveries and inventions that enable machine learning with artificial neural networks. So this one is actually, you know, it was actually not a breakthrough in physics. So this actually, for me, it's very surprising. But it was almost kind of a career recognition of the seeds that these 2 people planted in the field. So Jeff Hinton is actually at the moment reaching almost 1 million citations. So together with Yoshua Bengio, which is another of the godfathers of AI, he's basically the most cited scientist of all time. So he has broad recognition in the field of machine learning. And he also got the ACM Turing Award in 2018, which is the highest recognition for computer science. So now he has both the highest recognition in computer science and physics. Fun fact, actually he comes from a family of already famous scientists, so he's like the great-grandson of George Boole, which is like the founder of Boolean algebra. So if you study digital computers, you learn about Boolean algebra. And he has had a large influence because of also the students and postdocs that worked with him, including Ilya Sutskever, which was his PhD student, and it was the chief scientist of OpenAI, creators of ChatGPT. Yann LeCun, which was co-winner of the ACM Turing Award is the director of AI research at Meta. They work together. Max Welling, a lot of contributions on AI for science. So his impact also is noticeable through the network of people that he helped co-mentor. And the other winner is actually a physicist, John Hopfield. He had already been recognized by other prizes in the domain. So what were the kind of seminal ideas that they came up with, like in around the 70s or 80s, that were recognized by this prize? So one of them was this idea of Hopfield networks, so it really gets the name of one of the awardees. And in this summer school, you heard about neural networks, but mostly about feed-forward neural networks, so those in which you get some inputs, you predict outputs, but the outputs are not feedback again to the inputs. But those kind of architectures in which the output is fed back again to the inputs of neural network is called recurrent neural network. So these were actually an instance of recurrent neural networks. They dealt with binary inputs and output vectors, so just zeros and ones. And you could think of them as some sort of associative memory. So the task that they would accomplish was giving a noisy input, Boolean input vector, try to recover its denoised version. And the learning rule was not what you learned this week using backpropagation. Was more like a local learning rule that is actually more biological plausible. So backpropagation is not believed to be implementable by the brain. It's believed that the brain has much more local learning rules. So this actually, the neuroscientists call this the avian learning rule. And he was using that same principle. And it was also inspired by statistical mechanics, so spin glass models and so on. And that's where the connection to physics actually comes from. But like I said, it's a little bit surprising that this got a physics Nobel Prize, because actually the flow of ideas was the other way around. It was like physics inspiring machine learning and not machine learning having an impact on physics. But it was still recognized by this connection. The other contribution that both of the authors worked on was something called Boltzmann machines, which again had connections to statistical physics. And it was a precursor of what you now hear about generative AI. So generative AI is just models that learn to model a distribution, a statistical distribution of data. So rather than just discriminating between classes, like this is a dog, this is a cat, you're actually able to generate new samples from a distribution. And this was a precursor, like an initial version of those kind of models that was the seed to a lot of ideas that came decades later. So, and that was basically it for physics. It was really just a recognition. It was almost like a career prize, in my opinion. Now, in chemistry, the story was very different. In chemistry, the recognition was actually given to computational methods coming from machine learning that actually solved long-standing open problems in chemistry or organic or molecular biology. So here I have the picture of the three awardees. So David Baker from the University of Washington, and Demis Hassabis and John Jumper from Google DeepMind. So the committee justified the attribution by saying half of the award is attributed to David Baker for the problem of computational protein design, and the other half jointly to Demis Hassabis and John Jumper for protein structure prediction. So just to give an idea of why these problems involving proteins are so important, proteins, you can think of them as the workhorses of life in the cells. And actually we have, because they are so important, we actually have different names for different sorts of proteins that carry different functions. So enzymes, which are catalysts for chemical reactions, can be proteins. Antibodies, which fight infections in our body, are actually proteins. There are some hormones that are also proteins. There's structural proteins that provide support to cells and tissues. And there's also transport proteins that carry other molecules across cell membranes. For example, hemoglobin is a protein and it carries oxygen. So who are these two people? So Demis is the co-founder and CEO of DeepMind, which was a startup created in London around 2010 that got acquired by Google in 2014. I'll tell you a little bit about that story a bit later. But before that, he was basically a chess child prodigy. So he was like top 2 or top 3 of the world when he was like 11 or 10 or something. He studied computer science. He actually created a company implementing video games when he was like, I don't know, 16 or something. And then he went on to, because of his interest in artificial intelligence, he went on to do a PhD in neuroscience and actually studying the brain in more detail. And John Jumper is a computational chemist from the US that basically joined the group at AlphaFold more or less at the time I was moving on to something else. But he is was one of the lead research scientists that was really having some of the breakthroughs in AlphaFold that you will see later. So I said that they were given the prize for the problem of protein structure prediction. So what is that? So proteins can be described as a sequence of amino acids. You can actually, because there are only like 20 or 21 different amino acids in nature, you can actually represent them with a different letter in the alphabet and represent the full sequence of amino acids just by a long word, right, with potentially hundreds of letters. But what you care about is predicting its three-dimensional structure. So where are the positions of all these atoms that of each amino acid? Then it depends on how much level of detail you need. Sometimes you just need the backbone. You don't need all the side chains details. But that's the fundamental question, predicting that structure. By the way, a small distinction, when sometimes we talk about protein folding problem, it could imply that you are also interested in the trajectory, like the time sequence of how the change evolves in nature and the protein takes its fold. But this problem is a bit more specific. You just care about predicting the final shape of the protein. You are not trying to predict the full trajectory, how to get there. So to give you an idea of how we got to work at this problem at DeepMind, DeepMind had been acquired by Google around 2013 or 14 by a very strong result that impressed the research community, which was combining deep learning, so neural networks with many layers, with reinforcement learning, which is the field of machine learning that tries to learn like a controlled policy that maximizes the reward that you get by a series of actions you can take. So in this case, it was like a video console with many games, this Atari console. The actions you can take is like pressing in the buttons of the joystick, and the reward you get would be the score in the game. So the impressive result is that with this DQN algorithm, DeepMind was able to train from scratch without any human supervision, just by self-play, a policy that for many of these games would achieve superhuman performance. So this neural net would play better than human experts playing the game. So DeepMind actually had like 2 professional game players playing to get the human baseline and compare to those. So that's a nice job to have. And the year after, DeepMind got even more recognition because of the success with AlphaGo. So this was also a game, but it's not a game that typically you can be very reactive about, just like look at the board and predict the next move. It's a game that benefits from you having time to think. So if you think of the search tree of this game, which means at this player 1 has hundreds of, this is a 19 by 19 board, so you have hundreds of possibilities where you could place the next stone. the next move by your opponent will also have hundreds of those. And if you try to estimate the effect of how this chain of actions will unfold, you quickly are with a search tree that is very deep and it has a very wide branch factor. Much more so than in chess, which had been solved like by Deep Blue that beat Kasparov in, I think, 97, 98. Because chess has a much smaller branching factor, so the number of possible moves you can take at each time step are much lower. And so very briefly, the key insight there was to train a neural network, or basically two, that will help you search this big search space much faster. So one would help you decide, instead of considering all the possible next steps, just focus on the top most promising ones, let's say 5. And when you reach a certain depth, instead of going all the way to the end of the game to determine whether you whether you won or lost, which would give you the signal for the reward, you train a value network that estimates this probability with enough accuracy so that you don't have to unroll so much. And again, initially, this was actually initially trained using some human data, but then a version called AlphaZero was able to learn this with 0 human data and basically one day go from playing randomly to playing like superhuman. And I'm mentioning this because later I will connect this to some progress now in science. So at that time, this was like 2016, around February. At DeepMind, I was part of the applied research group, and there was like an internal hackathon in which managers tell you, okay, in the next 3 days there will be an event, just have fun, work in whatever you want. And so together with Rich Evans and Marek Barinsky, we decided to work on a problem that had some significance. Rather than being a game, it would be a scientific problem. This was the idea of Rich, actually. But it had very clear connections, or a formulation that could be gamified. So the University of Washington had developed this folded game, so actually from the group of the other Nobel Prize winner, David Baker, in which you have a representation of a protein, and you can play with it, drag and drop and move things apart and so on. And based on some energy function, some score that you can give to the configuration, like, oh, this is bad because you have some clashes here, things should be further apart because this should repulse with some electromagnetic force. So they are able to, given a configuration, give you a score. So we thought, okay, this sounds like a game. We have some action space, so you can move, you can change the configuration of the protein. You have a score. Let's try some of the algorithms that DeepMind developed on this. You know, not surprisingly, in 3 days, and we didn't get any breakthroughs, obviously, but it was exciting enough for the founders of DeepMind, both Demis and Mustafa, being excited about it, and basically we started working on it full time. So they told us, okay, stop doing whatever you were doing before. Now you will work on the problem of protein structure prediction full time. So a few people gathered, came from AlphaGo and from other projects and started working with us. So we started preparing to enter a biannual competition that happens since I don't know, maybe 2006? No, maybe earlier, so maybe 30 years ago, in which the whole community of computational biology is given a test. It's like every 2 years. It's like, so during that period, labs around the world determine experimentally the structure of some proteins, but they don't publish to anyone. It's kept secret. And then when the competition arrives, they say, okay, these are the sequences of amino acids. Please send your computational predictions to our jury, to our website or whatever, and then we will evaluate them, and at the end we will rank the teams. So up until that point, progress had been not great, like it was kind of flat. So this is the metric GDT. So if if you would make perfect predictions of each protein, you would get it's like 100% score, 100% accuracy. But it was kind of flat around 40, not making much progress. So, and this is basically the only part I really contribute to, in addition to the hackathon, was the initial version of the system that started to slightly beat the state of the art, which was basically the following. There, in the research literature, what they did was like a method called fragment insertion. So they would take a current configuration of the protein, look at a subsection, so a small fragment, let's say 5 amino acids or 10. They would have a fragment library with many different shapes and try to see, oh, what if I modify a little bit the shape to be a different one? Does my score, like this energy score that you saw in the game, get better or not? And then you search, you search, you search. So what we did to bring machine learning to this picture was basically replacing this kind of fragment library that was very handmade or not very flexible by a generative model, so again, like the precursors of generative AI, that would, given, if you condition on the amino acid sequence of that fragment, you could sample new likely shapes for that fragment. So then we would insert it, check the score, and see if it got better. And so this already started like showing some promise. And then when there was also some further work in terms of can we have a better energy scoring function rather than this physics base that we can learn? And so the people in the group created a neural network that would predict the pairwise distance between every amino acid, so this matrix n by n, and it would actually predict like some probability distribution of what was the neural network believe to be the distance between those two amino acids. And so this is where also John Jumper had a nice breakthrough, which then is described in our Nature paper in 2020, which is actually, if you have good enough predictions from this neural network, instead of doing this very slow search like trial and error, you could directly minimize like the negative log likelihood of the predictions of this neural network just by some gradient descent method, and actually converge to a shape of a protein that was like really good. You could not do these gradient descent methods in the original energy function. This would just give you like spaghetti predictions. So this was the initial breakthrough of AlphaFold 1. And so when we entered the competition, actually our submissions was a mix between those two systems. We actually won already the first competition we entered, and it was a little bit of a shock to the community because we were a team of just machine learning researchers and engineers without expertise in biology. We only had the advice of a professor from UCL, like once every 2 weeks, giving us some hints on how not to make big mistakes. Okay, so then for personal reasons, I moved from London to Zurich, so I stopped working on AlphaFold. But my colleagues worked on the next iteration, which was actually the one that is being recognized by the Nobel Prize. And they created a much more complex neural network, but it solved a major shortcoming of the previous architecture, which was in AlphaFold 1, there's a clear split between prediction from the neural network model and then an optimization algorithm. But the optimization algorithm is not learned, is not devised to benefit from the predictions of the neural network. What you really want is what is called end-to-end learning, is that your neural network predicts directly the outcome of interest, so immediately makes a prediction about the structure without having to do any optimization on top. So this involved, making things a lot more elaborate, exploiting these invariances or equivariances of the problem, like previous speaker said, distillation techniques, a lot of innovation. But this turned out to really, really be a breakthrough. So AlphaFold 2, when entered the competition 2 years later, basically achieved around 90 GDP score, which is getting closer to the accuracy level of experimental data. So it almost becomes like undistinguishable from actually measuring in the lab. So the organizers started saying that, yeah, this is basically a solution to a 50-year-old grand challenge in biology. But just to come back to the previous point, AlphaFold 2 was not like a single clever idea or a breakthrough. It was actually a combination of a lot of different techniques that helped a little bit. So this is an ablation study where you turn off and on and off some of those techniques and you see the impact. And really it was the cumulative contribution of many different small ideas that accumulated to get to that level of accuracy. And so I highlight this, why? Because if the team had to come up with 8 ideas that improved the system, they probably tried hundreds of those that didn't succeed. So this is pretty impressive. Since then, because it was so cheap now to make predictions about protein structures, people at DeepMind, jointly with the European Molecular Biology Lab, I think it's called Lab, they basically now predicted the structures for over 200 million sequences of amino acids that are known to science, basically. So now there's predictions for everything. And this is publicly available. So therefore, this triggered a lot of scientific impact. Like lots of researchers in these communities could benefit from this. So just for concluding the Nobel Prizes in 2024, David Baker, which is probably the most renowned scientist in this area of proteomics, leads the Institute for Protein Design at the University of Washington, was recognized by what you could think of the inverse problem of the protein structure prediction. So now you are not trying to go from amino acid sequence to structure, but the other way around. It's like trying to find out what is the amino acid sequence that would generate a shape like this, which could be, this is even more useful for things like drug designs or vaccines or enzymes, because you are trying to find what is the sequence I can synthesize in the lab to lead to this structure to have this function. And his initial contributions to this didn't even involve machine learning, because they have papers from, I think, early 2000s. But more recent work also builds on top of deep learning techniques they developed on their own lab. So they have their Rosetta Fold, which is like a similar system to AlphaFold, but fully developed by them. And so now they incorporate a lot of deep learning techniques also in their labs, and this was the, the recognition they got. Okay, so now I'm getting to the hard part. What could be the next Nobel Prizes? Well, first of all, I'm not going to talk about all Nobel Prizes, right? Because even though it's plausible that an LLM could write a good novel, I'm not going to venture into literature Nobel Prizes or to peace Nobel Prizes or even economic sciences. So I'm going to try to focus a little bit in speculating what could happen in physics, chemistry, and medicine. And later on, maybe a little bit of mathematics that does not have a Nobel Prize, but is also super promising. So when I was preparing for this talk, I was trying to think of what are the different kinds of breakthroughs that led to Nobel Prizes historically. It's hard to come up with a categorization, like I made up these titles, and it's hard, sometimes one contribution could fit in different clusters. But there had been things like discovering new phenomena, like for Pierre and Marie Curie, like discovery of radioactivity, maybe for Fleming in medicine, discovery of penicillin. Then there's the ones we think the most about, which is like fundamental theories, like Planck for quantum theory, Einstein, photoelectric effect, and then later, well, it was not the Nobel Prize for that, but then later the breakthroughs in relativity. There's things related to particle models and so on. Maybe in biology, I don't know how to classify this one from Watson and Crick on the DNA double helix. But then there's very different things as well that are very impactful. For example, there's Nobel Prize is attributed to novel experimental techniques that benefit science by what they can measure. So for electron microscope, there's a Nobel Prize. For magnetic resonance imaging, there's a Nobel Prize in medicine. There's even some examples of kind of, you could call them inventions that are not necessarily like experimental techniques in science, but for example, the transistor. So these people, Shockley, Bardeen, and Brighton, I think they were working at Bell Labs at the time and invented the transistor. They were recognized by this. It's almost like an invention, right? It's not a physical theory. And now, seems like, again, hard to categorize these contributions that were recognized recently. Is more like some sort of computational method that is very useful in science. So AlphaFold and this physics Nobel Prize. I think there's maybe a couple of other instances of sort of a computational model in chemistry before, but I don't, it's rare, it's rare. So just to highlight, why am I mentioning this? So I will place my bets not in some super intelligent AI that will have a brain like Einstein and come up with new theories. I will place my bets in much more grounded things that are already happening, and I will show some examples, and for which I believe that only incremental progress is required. Nothing magic or nothing crazy wishful thinking needs to happen. And I will give a lot of focus to contributions that come from the DeepMind science group, because this is actually, to the best of my knowledge, the bigger and most organized group actually tackling these problems. So DEM is even around 2016 when we were starting AlphaFold, he has a program. It's like, this will be a Nobel Prize factory. It's like, we will pick the problems that are of that scale and we will devote resources to it. And the way he talks about this is like, we focus on solving root node problems. What does he mean by this? If you think of the tree of knowledge of humanity, it's not all messy, it's not all equal, right? There's some more fundamental things, like you can think of mathematics and logic being at the foundations, physics building on top of mathematics, and chemistry, it's like physics at the molecular scale, and biology on top of these, and then you have I don't know, modeling living beings, and then you have modeling economics and sociology. So there's kind of a hierarchy, and even in each domain, you have problems that are much more impactful than others, right? So for the problem of protein structure prediction, it was one of those root node problems, because unlocking that problem can allow scientists to build on top of it, and that's why it has been so widely cited. People say that I think over 1 billion scientists now are using the predictions of AlphaFold in some way or form in their work. Okay, so now the bets where I can be wrong begin. So one area from physics where I think any kind of really significant breakthrough could lead to a recognition with a Nobel Prize would be nuclear fusion, right? So this is like potentially an infinite source of clean energy. And it has been very hard to achieve. So the theoretical principles, I guess, are understood by physicists. But it's very hard to build a machine where you can actually have this plasma well contained and the reaction to be sustained. So this is an area in which a group of DeepMind has been working on, which is how do you use algorithms from deep reinforcement learning, so very close to those ones that learn to play games, to actually control the plasma in a tokamak. So tokamak is this donut-shaped reactor, and it's I was going to say it's relatively easy to build. It's not true, because if you see this project, the European project, the ITER in France is like a huge thing. It's been built for several years. It's crazy. But it's like, you can build it, and then the problem is to sustain the reaction for a long time. And so here what researchers did was to, first using simulators of these plasmas, to learn a control policy. So instead of playing in a joystick to maximize the score of a game, would be like, how do I control the magnetic fields of these coils around the tokamak very quickly by taking some measurements of the state of the plasma to make it go for longer. So the score is like, can I keep the reaction going for longer? And so there's this paper in Nature, I think this is, yeah, already 2022, showing progress in this direction. The other kind of reactors that people care about are a bit different from tokamaks. So tokamaks are kind of simple in the design, but hard to control. And then there's these stellarators, which are apparently more stable if you can build one, but the design is much more complex. So deciding what should be these shapes of these coils that is really effective and that is also easy to build is a big puzzle. So actually at Innovative we have some researchers that are interested in this problem that are in touch with us, and we have integrated already a plasma simulator on our platform that people can experiment with. So instead of having a control problem, which is naturally tackled by deep reinforcement learning, you're more of a design problem that you need to solve in advance. But I don't know how the solution to this will come, but people are believing that because there are so many potential designs, it's possible that using machine learning could help you navigate that space. A little bit like previous speaker was exemplifying about the search space in chemical compounds. Here, the search space is big, but it determines the design of the reactor. Cool. So the other big area was covered by Jonathan's talk previously is material discovery. So in this problem, you have this very big combinatorial space of possible molecules, right? It's like almost unbounded because you can just add atoms, different types and so on, and recombine these can be very big. But like Jonathan was saying, there are some very impactful problems that you potentially could solve. One could be better materials for, let's say, battery with safer, higher energy density, faster charging batteries and so on. This would be very impactful. And people also have this holy grail of trying to find a room temperature superconductor, which, I mean, we don't know if there is one, but if there would be one, you would have zero loss power lines, right? Like could transmit energy without it dissipating as a form of heat. Could help in medical imaging, transportation, like magnetic levitation trains. Could help in quantum computing. It would be like, it's like their holy grail, right? And like we saw earlier, there's encouraging progress in this direction. So Meta just released this huge data set of simulations. So it basically has 100 million high fidelity simulations of different molecules. I think not only biomolecules, but metal complexes, electrolytes, so it's quite diverse. And there's been, again, published work already making progress on this, right? Like on using deep learning to predict materials properties, and like Jonathan was saying, even trying to simulate this evolving through time. So when you see the big labs collaborating with big universities to create such high quality and high volume data sets, you know that the machine learning community will pick up on this and iterate fast. Another one I'm mentioning here, because again, there's been published research from the DeepMind Science Group, is actually on achieving practical computing, quantum computing. So this one is actually a bit tricky. So this one you will see later. I'm a little bit less confident on this, because this is, improvements can come from two things. One is better hardware construction. So actually the way you construct this quantum computing is being different. And so recently Microsoft published a paper on their topological qubits that apparently have better properties. But you can also make algorithmic improvements, in particular to what they call error correction methods. So basically in quantum computing, you have this We don't have bits like we are used to here in logical classical computers. You have qubits or quantum bits. But the problem is that interferences because of heat or radiation and so on, the state of these qubits can really degrade in a way that is not desired to perform the computation. So what they do in practice is actually gather a group of several physical qubits and do some sort of error correcting algorithm on it to represent just one logical qubit. And so what DeepMind did was using machine learning techniques to learn a better quantum error correction algorithm. So this is super interesting again, because what they did was, again, first relying on simulated data. They had a simulator of quantum computing, generate lots of data on how those qubits could, the state could degrade, and then learn the inverse mapping. So this was cool because they showed that their neural network approach for error correction was more accurate than the previous baseline. But this is still not really applicable in practice, because running the neural network, it's a bit too slow for what you need in a real quantum computer. So here is a little bit trickier. The other one that is really, I think, obvious, right, is in medicine. So in medicine, when you are trying to cure infectious diseases, maybe with some antibiotics or even for cancer treatments or something, typically what you need to do is design a new molecule. Could be a biomolecule, or it could be some small compound that typically will bind with some target protein in the cell. So again, this is very, very similar and very adequate for machine learning methods, because we are again in the kind of problems where you have a very big space, very big search space. It has structure, and you are trying to kind of find a needle in the haystack, and you can benefit from the speed-ups that machine learning methods could yield, like Jonathan was showing for materials. This is also applicable for drug design. And you can see that this is coming because, in particular, DeepMind has now a spin-out which is called Isomorphic Labs, which their sole goal is to do AI drug design. So this is, and they are partnering with very big pharmaceutical companies already that are putting a lot of money into it. And I did mention before, but there's already a more recent version of AlphaFold, AlphaFold 3, which, in addition to predicting structure of a protein in just caring about that structure, is actually now able to model more biomolecules in the body, including DNA or even ions or other proteins. And you can start modeling how they bind and how they interact. So this is what really starts to become useful for therapies, for drug design or others. Cool, let me check time. As you know, there is no Nobel Prize for mathematics. The most renowned prizes in mathematics are like the Fields Medal, which is attributed to mathematicians with less than 40 years old. There's the Abel Prize, which is a little bit analogous to the Nobel Prize, but is more recent. There's the Breakthrough Prize that gives a lot of money, but also more recent. And there's also these 7 Millennium Prize problems for which a solution to any of those would be rewarded by $1 million, I think. And so far, only one has been solved, so the Poincaré conjecture. And even though it's Nobel Prize, I figured it would be cool to talk about a little bit about mathematics before I end my talk. So here we have been seeing very fast progress. So just, I think a few months ago, again, the DeepMind Science Group achieved quite of a feat. So if you are not aware of, there is this International Math Olympiad, which is a competition that happens every year. and that gathers together some of the best young mathematicians. So it's like, this is for like high school students. This is very, very hard. I actually know by first-hand experience, because in the year 2000, I was among the best in Portugal, so I represented Portugal in South Korea in this competition, and I was terrible. I was basically there, like scoring almost no points, very little points. It's like, you need to be super smart, but also know a lot of different techniques from number theory, geometry, and so on. And by the way, if you get a Nobel Prize, gold medal there, which is given to basically the top 8% more or less of competitors, is a very good predictor that you will do well later. Like many of the field's medalists, they were like gold medal winners in the Math Olympiads. And so DeepMind developed a system that basically would score at silver level, just getting to gold already. And now they use alpha something for everything, so this is called alpha proof. And they also had a more specialized system for geometry problems, which are a little bit different, and you can exploit more the properties of geometry if you design a specialized system. But fundamentally, what is interesting is that they came up with a way to formalize these problems in a language that, if you find a solution, is verifiably correct. So it's not, typically when you solve a problem, the statement is written in English, and then you make a proof in English with some formulas and so on. But there's something called the lean language, or lean theorem prover, which is a formal specification of mathematical statements that you can express any statement in mathematics, and if you have a proof, you can verify it's correct. I'll show you later, but from this point onward, this is basically using the same algorithms of AlphaZero, like the one that learned to play Go. And more recent, I don't have time to go over this, but DeepMind also developed some similar systems that can contribute both to mathematics and computer science. So these ones kind of are able to come up with new algorithms. Sometimes it can be just optimization algorithms, but sometimes they are able to find like matrix multiplication algorithms that use fewer instructions and so on. So this is a very active area of research. To the point that just, I think last week or something, Terence Tao, which is like probably, I don't know, for many people would say is the best mathematician alive and the most recognized. So not only was he like one of those child prodigies that won gold medals, he got the Fields Medal, got the Breakthroughs Prize, and so on. And now he's very interested in AI proof methods. So he started collaborating with the Google DeepMind to explore this kind of systems and see the impact it can have on mathematics. And this is David Silver. I recommend you watch this YouTube video on the importance of reinforcement learning to go to superhuman performance in some domains. Basically, what he's already saying is, AlphaZero is basically now playing the game of mathematics. And he says, there's really no fundamental barrier to breakthroughs now in this. Because the system doesn't need to know about the physical world. Everything is digital, everything is specified. The source of success is completely verifiable, much like in a game of Go, you know whether you won or lost. Here, you can, if you generate a proof, you can check it's correct or not. So basically now this is to the point that it's a matter of throwing computation to it and solve bigger and bigger problems, potentially improving some parts of the system to be even more effective in that search space. But basically, to the lead researchers in this area, it's like there's no fundamental barrier now. Cool, so what is I'll just conclude with maybe the main insight, is that machine learning is very good at finding structure in very large spaces, assuming you have very high quality, very reliable sources of ground truth to ground the system on. So in games, it was like the score, or did you win or lose? But in science, it can come from maybe 3 different sources, right? So if you have really very good experimental real data, which was the case of AlphaFold, that we had we had like tens of thousands of good protein structures that were determined in the lab, okay, you just use that. You are on the lucky path. If you don't have that, you might need high fidelity simulations. This is also one of our core beliefs at Indutiva, right? We are building the platform where it's going to be very easy to generate data sets based on numerical simulations, and you can even do it cheaply and customize to your domain. But we saw here the example of Meta that they use like millions of core hours to generate this data set. So this can be used to ground the models to learn something meaningful. Yeah, and finally, like I said, in the domains of math and maybe even computer science, does not even need experimental data or simulations. This is just grounded on axioms, or can be grounded on existing theorems that were proved by humans that you can also build upon. Even if the system didn't prove it, it can rely on it. So, to conclude, notice that I didn't say we will need any AGI, artificial general intelligence, or superhuman intelligence. Nothing mystical. I'm not talking about an AI scientist that has like the same cognitive processes as us. I'm just saying for these problems, incremental progress will be enough. And so to make it more concrete, if you read this book on super forecasters, they tell you, if you want to make predictions, you need to be a bit concrete, right? There needs to be some statements that are either true or false, and assign some timeline to it and some probability of your belief that this will happen. The idea is that if you are high confidence on something and it's wrong, you lose a lot of points. Like you are deluded, right? You are super confident about this, you made the wrong prediction, you lose a lot of points. However, if you predict correctly and you are high confidence, this also gives a lot of points. If you make a low confidence prediction and you are right, okay, you gain a little bit of points, but not much, right? Anyways, you're low confidence, right? You can say you are low confidence about anything. And in the same way, if you are low confidence about something and it didn't go in your direction, you don't lose too many points. So here I'm just like highlighting my beliefs now. I'm cheating a little bit because these statements are not concrete enough, right? I'm saying an AI-designed drug curing a major disease. To be more specific, I would have to say, you know, there will be a drug for malaria or something, come up with a number. So I'm kind of benefit from this ambiguity. Also for the material with incredible properties, or what is the problem, the unsolved math problem that will be solved. But anyways, to quantify a bit, I'm pretty confident on this one, so that in the next 5 years, like an AI drug design will cure some major disease. So I'm like, I say with 80% probability, I believe this will happen. Likewise for AI design material. Actually, I was waiting for today's talk to see if I would need to update this number based on what Jonathan would say, but I'm keeping it at 0.8. In math, I'm actually more confident because, you know, like David Silva was saying, there is no fundamental barrier there. There's no the bottleneck of trying to check with reality. It's all digital. And then I'm less confident on the other ones because, like, for nuclear fusion, it's a very big piece of hardware, like very complex, and even though it could happen, I'm saying 20% probability. Probably the breakthrough might not come from some AI contribution, so that would be decrease even my estimate to lower number. And likewise for quantum computing, you know, I don't know if this will happen in the next 5 years, and maybe it will be a breakthrough in hardware, not AI. But yeah, these are my forecasts, so reach out to me in 5 years to tell me how wrong I was. And yeah, thank you.
Okay, thank you, Hugo, for your presentation. I hope you're right in most of your predictions for the upcoming years.
It's a fantastic time to be alive, right? If any of that thing happens, my goodness.
Exactly. So now it's time for room to the audience to raise questions to Hugo.
Can I ask a provocative question?
No, next question.
What is the chance of being a Portuguese person?
Oof. Well, for this kind of things, I think low, because these tend to be things that will be conducted by a strong group. So, for example, in the case of AlphaFold, I think I had it in some slide. The AlphaFold 2 paper has like 45 co-authors or something like that, for some around that number. And obviously, the only two that were recognized were representatives of this group. Was John Jumper, which was the kind of the lead researcher. He had some of the breakthroughs. And Demis Hassabis was recognized because he's like the leader of the organization itself, right? He was not actually coming up with the breakthroughs, but he was like coordinating this effort. So what I believe is that these kind of breakthroughs will be results of kind of elite teams that have very talented people that have nearly unlimited resources in terms of computation, and that can stay working on the problem to enough time to get this level. So for AlphaFold, it took 5-6 years of focused effort. People were doing nothing else, very focused and doing this. Yeah, maybe João here is a physicist. So I would like to say my brother could win a Nobel Prize in Physics, but it comes from the theory field, so it will not be AI field.
There are many examples. So, for example, there is a Portuguese researcher that works in Germany and is leading the search with artificial intelligence for high-temperature superconductors. So this is a huge program from the Munich University, and the leader is a Portuguese researcher. In our New Talents in Physics programs, we have some young researchers tackling the problem of confining the plasma, finding the optimal magnetic fields, and they are working with artificial intelligence. So no one exactly knows which team will get the best result, but you never know.
Exactly.
Yeah. Okay. Yeah. So all these conditions have to be aligned in order to.
Yeah.
Computers now are really available everywhere. It's quite easy to get, even if you are in a peripheral country. So I think most important is ideas and how to tackle.
Oh, I'm getting another provocative question now from my co-founder. Okay.
So it's a provocative follow-up on a provocative question. So, and what do you think are the chances of those Nobel Prizes or Nobel Prizes awardees coming from industry versus academia?
Yeah, exactly. That's a good question. I think for many of these, at least the ones I illustrated, is more likely to come from industry labs. And yeah, the reasons are similar, right? Like easy access to talent, to computational resources, not being distracted by other responsibilities, I don't know, administrative or teaching. And also a key component, which I think was really important for AlphaFold, is not only having scientists, but having very good engineers. So I was a research engineer, so I was not a research scientist, but in DeepMind you have a lot of these, like people that know the principles of machine learning, but then know how to implement this in practice and scale it. And in universities, you rarely have the ability to hire for these positions. You have professors, you have scientists, you have postdocs, PhDs, but it's almost impossible to have the best engineers because they will. First, that role does not exist, and if it did, it would be a tenth of the salary of industry, so it's much harder. But from academia, there can maybe other breakthroughs, right? Much more even elegant or intellectual, interesting can come. The ones I highlighted here is almost like if you devote a well-funded team with enough time here, this can happen. It's not like nothing magic needs to happen. But most of the Nobel Prizes are of the other kind, right? It's just like brilliant ideas that come out of anywhere, right? There's a question here. Oh, sorry.
Thank you. So in the beginning, you said you'll discard the contribution of AI to the philosophy, literature, and socioeconomics. But what would you think are the bigger limitations of AI so that caused you to discard those fields?
Well, actually, this was mostly a matter of the audience and the scope of the school. Let me think. So, for example, in economic science, I don't know, there's many contributions that are like algorithmic, right? So these kind of game theory things and so on. So it's not unseen that they value these kind of contributions, but to the best of my knowledge, they don't tend to be so data-driven, but there could be opportunity there. In peace, I have a hard time an AI contributing to negotiating world peace, but who knows? In literature, it's an interesting question, right? Because that could be really happening now in the sense of everybody is able already to generate text using LLMs, and sometimes things are high quality. Now, these systems have been trained more to generate useful answers, right? Because that's the scenario where they are most like monetizable and have more impact in the economy. They were not really trained to be delightful in terms of reading experience and have this artistic feeling. But could happen. I mean, people could start using LLMs to publish books under some pseudonym, and one of them could take off as being considered brilliant. The limitation there is that, again, I show that in these other systems, you have very strong grounding. You either have a score, or you have axioms, or you have physical laws, or real data. For literature, this is a subjective judgment, which is based on human experience. So you'd have to have enough quality labeled data of the tastes of humans with respect to novels to try to bias the system to somehow generate this kind of novels, but it's possible.
Okay, thank you.
What's your guess on an AGI, technological singularity? So I know it's hard to say, but what's your guess? Will it happen? When will it happen? Next years? Next decades?
Well, the problem there is that sometimes people don't even agree on the definition. So AGI was a term originally introduced by Shane Legg, which is one of the co-founders of DeepMind, because in his PhD student years, when he was in Lugano in Switzerland under the supervision of Jürgen Schmidhuber, one of the godfathers of AI, jointly with Markus Utter, he started trying to formalize what is intelligence. And so he collected a series of definitions from dictionaries, encyclopedias, and so on. And roughly, not very precise, but the definition was something is like a system that learns to perform well in a wide variety of environments. It's kind of along those lines, right? So when he then founded DeepMind and started working on deep reinforcement learning, he said, okay, let's benchmark under this vague metric, let's do the following. Let's create a lot of different environments, a lot of different tasks, and see how well the same algorithm will do in this variety of tasks. So this will somehow capture this, right? It's like you need to learn, and you need to learn to do well in a wide variety of environments. So that was the general comes from. And so this would just become more and more general. To some extent, if you limit yourself to the environments where you can communicate by language, like question and answering and its language, I would argue that we already have AGI, because there is, at the moment, there is no single human that would be able to give the same quality of answers that these systems give, right? Because they can speak in any language, they can talk about any topic, and if, so they are already more general than humans within that interface, which is contrasting to what it used to be before. Before you would critique AI by being narrow. It's like you make a system to play chess, it does not do anything else than chess, so it cannot do anything else. But now by this notion of generality, if you're just talking about a text interface and question answering, these systems are already way more general than any human, right? So we are becoming the specialists. Maybe, I don't know, you are better, I don't know, in computational fluid dynamics or something from your culture. But if you average about all possible questions that you can ask to the system and give a score, it's already way more general than us. So in that sense, we already have AGI. The question is, if you want to go broader, like to have, humans don't just write text, right? So humans perceive the world like natural vision, they hear, they speak, and notably, they also move around, right? And for example, in the field of robotics, which is trying to solve the problem of locomotion, it's still very behind animals or humans, right? And what seems to be key there is that mastering fluency of language is not enough. You need to have a model of the world. So model of the world means you are given a representation of the current state, and you need to predict, if I take some action, what will be the next state. So this is also the formulation in reinforcement learning. So this means learning like intuitive physics. Like I know that if I touch this, maybe this bottle of water will fall. I throw something with a given strength, I can estimate, I can expect where it will land, and so on. And large language models now, they are trained basically on text data, sometimes the images, but they don't have a truly grounding in the physical reality. So whatever they can learn about a model of the world is a little bit implicit. It's just like whatever is described by language and maybe some images, they can start having some emerging representation of the state of the world. But many things are not there because, you know, a baby is learning moving around, but maybe this is never described by language, right? Or we saw these examples of physical reality, right? How do you describe, there's not a web page describing the quantum reactions of material, right? Yeah. So what people believe to be the missing ingredients, for example, Jan Lecan from Meta and Facebook AI research believe, is that the missing components is like effective ways of learning a model of the world, which then you can use together with a planning system. So not only you are able to predict what happens, you are able to come up with a plan. If I do this and then that and then that, this will be the effect, which brings you closer to what AlphaGo does in the Go board, which is I do this and that and I plan. But now you would, instead of being a very contained game where the model of the world is very clear, you'd have to learn this just by observation of the data, and this is where it's still challenging. Yeah.
Thanks.
So I'd just like to add something to what Hugo said. So there's also one aspect that people don't usually talk about when they talk about intelligence, which is the energy cost of intelligence, right? And this is an important thing when you think about the real world. So it may be the case that humans are the most intelligent thing ever in the universe on a per watt, so power, right? Energy on a per watt basis, right? Because our intelligence is optimized in terms of the amount of energy that we have available, not just by sitting here and thinking, just in terms of words, but also movement, right? The ability to act on the world. And that's a really interesting thing that if we're talking about general intelligence, we also need to account for the energy cost. And I'm not even talking about geopolitical stuff, about data centers and all that. I'm just talking about the definition of intelligence, right? Because it has to be a function of energy, right? So, and this becomes really interesting when we go to the real world. Because one thing is to have a data center that it's able to eat a gazillion of words and has, whatever, algorithms, transformers and all that. And it's fed by a nuclear plant that can inject as much energy as you want, or, well, within some bounds, of course. And another thing is navigate in the physical world where the mere act of navigation, of walking around, consumes energy too, right? So I think then the question becomes, it's not whether we're going to have general intelligence or some sort of intelligence, is how can we have that sort of intelligence in a way which is compatible with the amount of energy that we can use to achieve that intelligence, right? And humans are really good at that. And animals and living beings are really good, are super smart. Like a cat is super smart per watt, right? per unit of energy, or power, right? Consumption, right? That's the key thing. So when we go now to the real world and we have robotics, it's going to be very difficult to have intelligent robots with the same level of energy efficiency. And that's difficult. So when sometimes people think about, the Terminator scenario, where it's going to be Terminators coming after humans, well, you just need to plug to just push the plug, right? Because they cannot survive without energy. We still haven't found a form of natural intelligence that is energy efficient. So it's just to add one more layer to when is this going to happen? It's a too abstract of a question. It's when is this going to happen, if ever, but let's assume that it will, based on a certain amount of energy that we're willing to invest to achieve that AGI.
Sorry, Philippa, she keeps running from one side of the room to the other side. Just to make a comment, I think you forgot to list the Turing Prize, did you?
No.
That's at the level of Nobel Prize for Mathematics.
Yeah, Turing Prize is the more recognized prize for computer science. So some of the people I mentioned here got the ACM Turing Award Prize. And I think one of the latest slides that I showed, those systems like FunSearch and AlphaEvolve are actually outputting new algorithms, so they could potentially be contributions to...
Yeah, but in your list at the beginning you mentioned the Millennium Prize, but not Turing was not there. I think I noticed that.
I was talking more on mathematics, not so much on computer
And the
science.
Turing Prize is quite a big award. Also, because this is an AI course, I was asking ChatGPT, what are the conditions that lead to a Nobel Prize? And it gave me 6 conditions, which I'm not going to read now. I think this is coming to an end. And they are quite interesting. And the last one, it has to be in line with the Alfred Nobel's will, which was quite vague. What is in this? But anyway, I'll leave the people to go and ask ChatGPT and give you the question.
They should
And the 6 conditions to work.
They need to be things that contribute to the advancement of humanity, right? And, yeah.
Well, I can just give you the headings if you want. So Nobel Prizes are awarded to individuals. That's number 1. No, sorry. The conditions are groundbreaking discovery or innovation. That's condition number 1. And then it goes, what do they mean by this? What does it mean by this? And condition number 2, demonstrate impact over time. That's why usually this is given to old people. Scientific consensus, so the community has to accept that this is good. Individual contribution. Nobel Prizes are awarded to individuals, maximum 3, not teams or institutions. And nowadays, most other research is a group work, not individuals. Eligibility and nomination. If you are already dead, you cannot have the Nobel Prize, you know that. And of course, it has to be in line with Alfred Nobel's will.
I think for example, Nobel Peace Prize, it has happened, it was attributed to institutions like UNICEF and so on. But for example, AlphaFold was quite surprising in that respect because it just took 4 years from the groundbreaking result to the recognition. This was very, it was the thing that surprised me. I always expected this would happen as a recognition, but not just 4 years after. That was very surprising.
If there are no further questions from the audience, let's congratulate Hugo again on his presentation. Okay.
All right, and this...
Felipe has asked me to say something about the closure. I was not ready for that, but anyway, all I have to say is thank you all for coming, and I hope you enjoy all this week of hard work, and also some talking, and I heard some of you went for a drinking, so it's a full week, and I hope I can see you again. Let's thank Hugo.